Good afternoon, everyone. Today we're going to solve a 3x3 system of linear equations by substitution. So, to start things off, we really want to do the same thing we do with the 2x2 system of equations. We want to isolate one of our variables, right? And we're just going to start substituting into the other equations we haven't used yet and try to bring a 3x3 system down to a 2x2 system of equations with two variables so that we can solve for those two variables because we are hopefully now comfortable with 2x2 systems, okay? So at first glance, our first equation gives us two variables that have a nice coefficient of 1, right? Those are super convenient to isolate, and so it's really just up to us which variable we want to isolate. It really doesn't matter which one we pick. I'm going to pick arbitrarily the x. So step 1, let's isolate that x. 1, isolate x in equation 1. When I circle 1, that means equation 1. Okay? So if we want to get the x by itself in this equation, if we want to isolate that x, let's move everything else on the other side. And so we'll do minus y, minus y, minus y. Sorry. Minus 2z, and then minus y and minus 2z, of course, right? To get x isolated on one side. And so x is then negative y minus 2z plus 6, okay? And now, what we can do is substitute it into equation 2, into either of the equations we haven't used yet, okay? This one looks not too hard to work with, so that's gonna be my next step. We do have a lot of freedom in where we substitute in our isolated variable. You're just going to get a knack for it the more you do some practice questions. So let's sub it into equation 2. To sub in equation 2, right? So now that x is going to literally be replaced with this expression that we have for x, right? We're going to substitute in an expression we got for x into x in a different equation. And so now equation 2 is going to become negative this stuff, right? Negative x, so negative all of that stuff, because that is equal to x. So negative y minus 2z plus 6. And then we solve everything else. Plus 2y plus 2z is equal to 4. And now we can simplify this a bit. So we have negative, so we have y plus 2z minus 6 plus 2y plus 2z is equal to 4. We can combine the y's, we can combine the z's, and then we can add 6 on both sides, which would mean that we now have y plus 2y, 3y, 2z plus 2z plus 4z being equal to 10. And this is a new equation, right? So let's call that equation 4. So far we have equations 1, 2, and 3 is the original 3. Now we're creating new equations out of this linear system, and so let's call this equation 4, okay? I always call my new equations because now we can easily reference it later on in our solution, okay? Really good idea. Now, this is one equation relating the variables y and z. We have one equation now with two distinct variables. Now, the rule of thumb is always the same. We need as many independent equations as we have variables to solve for to be able to solve for a unique solution. And so we have one variable with y and z. We need two to be able to actually solve for y and z. So now we can plug this x that we got also in equation 3 because we got an expression for x using equation 1. Let's plug it into 2 and 3, and we'll get two separate equations. The x will be gone, because x will be in terms of y and z. So we'll get two new equations with only the y and the z, right? Because we'll have y and z, and the x will now be in terms of y and z. And so we'll get two equations with y and z, enabling us to solve for y and z, okay? So now, step 3, sub into equation 3. Right? The one we haven't used yet. So let's plug that x into here now. And so, in doing so, we're going to get 5 times x is going to be this expression. So negative y minus 2z 6, and we still have all the rest, plus 3z is equal to 7, right? Now let's clean this up. The 5 multiplies through the bracket always, and so negative 5y minus 10z plus 30 minus 3y plus 3z is equal to 7, right? That's a mean looking equation. Let's combine our like terms, negative 5y and 3y. We have negative 10z plus 3z, and let's subtract 30 from both sides to get rid of it on the left. Now, negative 5y minus another 3y means negative 8y, and negative 10z plus 3z means negative 7z is equal to 7 minus 30 means negative 23. And this is a new equation again, so let's call it equation 5. Okay, so now we have a second equation with these same two variables. And so what we've successfully done is we've reduced the 3 by 3 into a manageable 2 by 2 system of equations. And hopefully you know how to solve that, right? I'm gonna write it over here so that we can easily see it in our brains. Negative minus some z is equal to negative 23. Call that equation 5. And now, right, we have a manageable 2 by 2 system of equations. This needs to be automatic when you get to this step, right? This is a big success. So now we can use elimination or substitution, whatever you rather. Let's use substitution since we're practicing substitution. Is there any variable that looks easy to isolate? Not particularly. I'm just going to choose the smallest coefficient. I'm going to choose the 3. So in here, I'll have 3y is equal to negative 4z plus 10. And so divide by 3, divide everything by 3. We get y is equal to negative 4z over 3 plus 10 over 3, right? So we've isolated that y. Okay, and now with the 2 by 2, we know where we have to plug that in. We have to plug it into the other equation that we haven't used, right? So let's go ahead and do that. So now we're gonna have negative 8y. Y is that thing over there. So negative 8 times negative 4z over 3 plus 10 over 3. And then we still have the rest. Minus 7z is equal to negative 23, right? And I know this looks tricky, but we're getting to the end here. Now let's multiply through. So the negative 8 multiplies through. So we get 32z over 3. Negative 8 times 10 minus 80 over 3 minus 7z is equal to negative 23. And I know this looks daunting, but at least we only have one variable here. Right? We only have one variable, namely the z, to solve for, and so we can actually get a value for it. So let's combine our like terms. 32 over 3z minus 7z. So we'll do 32 over 3z minus 7z is equal to, let's add 8 over 3 on both sides, plus 80 over 3. Negative 23 plus 83, I'll just make a side note here. Negative 23 is equal to negative 69 over 3, right? And so if we want to add those together, getting a common denominator, negative 69 over 3 plus 80 over 3 is going to be positive 11 over 3, right? And likewise, that's 7z. 7z is equal to 21z over 3, right? Just side notes to keep in mind. So again, to add these two terms together, we need a common denominator, and so we get 32 over 3z minus 21 over 3z, and so that means that we have 32 over 3 minus 21 over 3z, which is 11 over 3. Z is equal to 11 over 3, and finally, our life can be simplified again. We can divide both sides by 11 over 3, right? And we get a nice value for z. Z is equal to 11 over 3 divided by itself, of course, means that z is equal to 1. We've only found one of our 3 variables, but that is the hardest one to get, once we have one, the other two kind of fall into our laps pretty quickly. So we have that finally z is equal to 1, and up here we found a nice convenient expression for y in terms of z, right? And so we can literally just plug in the value of z that we found into this and solve for y pretty quickly. So let's go ahead and do that. That z is going to become a 1, right? And so y is going to be negative 4 times 1 over 3 plus 10 over 3, right? Again, substituting in the value of 1 in for z in our expression for y in terms of z. And so y is negative 4 over 3 plus 10 over 3. Negative 4, we already have a common denominator, right? So negative 4 plus 10, that is positive 6 over 3, and 6 over 3, of course, is 2. Okay? And now we have z equal 1, y is equal to 2. We have 2 of our 3 variables. We need to use one of our original 3 equations where we have all 3 variables inside of one equation to solve for our x at the end. Or we can even plug it into this nice expression for x that we developed at the very beginning. Let's go ahead and do that. That seems like our best bet. Let's plug in z is equal to 1, y is equal to 2 into here, okay? And that's going to mean, let's do that over here, x is equal to negative y, so negative 2, minus 2z, so minus 2 times 1, plus 6, right? Subbing in our y and z values that we found, and solving for x, so x is negative 2 minus 2 plus 6, x is negative 4 plus 6, and finally, we find that x is equal to 2. And we are done. So, after finding an expression for x in terms of y and z, we were able to substitute that in, that expression for x, into the x in equations 2 and 3, the 2 equations that we hadn't used yet. With those 2 equations, we managed to create equations 4 and 5, which were 2 equations with only the y and z variables, right? And this right here is a 2 by 2 system, right? This right here is a 2 by 2 system of linear equations, right? And so now you can go back to your regular substitution with 2 by 2, solve for z, even though we're dealing with fractions. Once you find z, substitute it in to either of the equations or in the equation for y that we created here, find your y, and then use your use your values for z and your y, plugging them into the expression for x that we derived at the very beginning, and that allows us to solve for x. Over here, getting that x is equal to 2, z is equal to 1, and y is also equal to 2. You can verify your solution by plugging all 3 values back into all 3 equations, making sure they're all 3 simultaneously satisfied, and I assure you these ones are correct. So I hope this starts to make the connections. I hope you find the substitution method most efficient. That's certainly how I feel about it, and thanks for watching.